everyone, my name is Subordinate Barry from Barry Science Lab, and welcome back to Probability. Today is Probability Lecture, I think, five. And today we're going to be talking about expectation values. And to do that, we're going to have to talk about random variables. All right. Sometimes you want to measure an event or the result of the sum, for example, of two random events. But that itself is not caused by an event. So you can't write it as P of E. Essentially, let's say, for example, you want to know the chances of rolling a 7 on two dice. You don't care if it's a 6 and a 1. You don't care if it's a 5 and a 2. All you care about is that the sum is a 7. And so that can't exactly be written as the probability of event 1 plus probability of event 2. Instead, we're going to have to make up a variable. Let's call it x for the result of this dice roll. X is a random variable because, its value is random. There's a chance that it will be given a certain value and a chance that it will be given a certain other value. So, how do we measure the chance that a random variable will be assigned a value? Well, for x in particular, x is a discrete random variable. What does that mean? You cannot roll 6.5 or pi with two dice. With two dice, you get exactly 11 options. 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12. Note how there is no 1. So, that means that there is absolutely no probability you will get anything in between these, like 10.5, or pi, or the square root of 2. The only possible values you can get are these, a finite number, or it can also be countably many numbers. For example, you might be asked to give a random integer, and in that case, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, there are countably many. So, we call it discrete when, it's discrete. Formally, when the measure of all the points where the probability mass function is not 0 is equal to 0. What is the probability mass function? Okay, so this kind of works like a probability density function, if you've heard of that, for discrete variables. So let's first of all, this is dying. Let's first of all write out what the chances are of getting a 2, 3, all the way to 12. Now we're working in one of those easy cases where not all of these have the same chance of occurring, but you know that the chance of you getting A and B is the exact same chance as you getting any C and D. Both 1 over 36. So you just have to count how many ways A plus B can be equal to a certain number, and then divide that by 36. So in this case, how can we do that? Well, let's take a particular number, say 7. We start from 6 plus 1. Then we move to 5 plus 2. Then 4 plus 3. And then you'll note that the other 3 ways to write it are reversed. But they still count. Because, of course, you can get a 4 into 3, and then you can get a 3 into 4. So, since there were 6 ways to write it, I don't have 6 fingers, unfortunately. unfortunately. This is 6 over 36, which is a 1/6 chance of happening. Now, you might think this rule applies for everything. Isn't it just going to be n minus 1 over 36 chance of rolling n? Well, let's try adding everything up and seeing if that holds. 1 over 36 plus 2 over 36 plus, you know what, I'm bored, let's speed it up, plus 11 over 36. Oh, wait a second, that's 66 over 36. So obviously that can't happen. So instead, when we have 8, it's not like this becomes 7 plus 1 and then 6 plus 2 and so on. We have to eliminate that and start with 6 plus 2, 5 plus 3, 4 plus 4, and then we flip the other two, which gives us a 5 over 36 chance. And you probably have a feeling in your bones that 9 has a 4 over 36 chance. 10 has a 3 out of 36 chance. 11 has a 2 out of 36 chance. And 12 has a 1 out of 36 chance. And that would be exactly right. So, what does the probability mass function look like? Well, something like 1, 2, 3, 4, 5, 4, 3, 2, 1. Oh wait, no. 6, 5, 4, 3, 2, 1. I need something. Yeah, red marker. I already have a blue one. Red marker is no more. Oh. Okay, sure. So we took them out back. This is what we call the probability mass function. So what's going on here? Well, everything that's not highlighted with a line is where it's 0. Everything that is highlighted, well, this is 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So this is the chance that x is equal to a given number. That's what the probability mass function tells us. And here it's kind of the sum of a bunch of delta functions. Well, not really delta functions. It's the sum of a bunch of spikes. If you ask me for the probability of getting pi, it's 0. You can't get pi from a dice roll. If you ask me for the probability of 8, I can happily tell you it's 536. Now there are situations where I would be able to tell you pi. For instance, if we added pi minus 1 to every single roll, then that would give you a 1 over 36 chance. But having pi is not the criteria for being continuous. Being continuous means that formally, the set where this probability density function is equal to 0, or not equal to 0, the measure of this is equal to 0. Wait, no. So this is the criteria for being discrete. If this is not true, then it's continuous. Alright, so that's the probability mass. But what's the expectation value? Well, as you might expect, it's the average value you might get from a dice roll. So if you roll the 2 dice 100,000 times, then your average should converge to the expected value. That's the law of large numbers, and we'll be proving it later. But for right now, the expectation value of a random variable x is equal to the sum x p of x for all possibilities that x can have. Here, there are 11 possible values that x can take up. So, you can write something like, I don't know. Oh, wait. What do I mean? I don't know. I do know. 2 times 1 over 36, that's the probability of getting a 2. 3 times 2 over 36. 4 times 3 over 36. 5 times 4 over 36. 6 times 5 over 36. 7 times 6 over 36. It's kind of like a mean. Sorry. 8, 5, 36. 9, 4, 36. 10, 3, 36. 11, 2, 36. 12, 136. Now, the secret technique is realizing that all of this sums up to 14 times 136 plus 14 times 236 plus 14 times 336. Just think about it. Plus 14 times 436 plus 14 times 536 plus 7 times 636. And then you can really just chop this up, and the expectation value becomes what? 14 times 15. 15 plus 6 over 72. 15 over 36 plus, 14 times a half, which is 7. Which means this is one of those rare cases where the expectation value is actually equal to the median, or the most likely outcome. One more thing to look at is that the expectation value of, for example, if you roll n dice, the expectation value will be equal to n multiplied by the expectation value that you get when rolling one die, which is 3.5. You can see it happening here because it's 7 when we roll 2 dice. Okay, so that's what expectation value is, at least for discrete probability distributions. Tomorrow, we'll explore what this looks like for continuous probability distributions. And one last thing, I did say that it can be countable. There can be countably many points, and even if there's an infinite number, this formula still works. You might say, well, how does that make sense? Won't the expectation value be infinite? Well, let's say there's a 1/4 value that I choose 1, a 1/9 value that I choose 2, a 1/16 value that I choose 3, and so on and so forth. Actually, I'd have to normalize these because, what is this? I've got to keep it secret, so I'm intentionally blocking. Okay. So, what would it be? Okay, that's actually really easy to guess. But I'd have to write something like this, but even then, this still makes sense. 6 over 16, pi squared minus 6, and so on and so forth. And, the sum of these probabilities is 1, which means that, by the Basel problem, which means that the sum of all of these is 1. I have to pick some integer. But, of course, the chances that that integer is a low one are extremely, extremely, extremely likely. And this summation still works. Wait a second. No, it doesn't, because the probability mass function is 1 over n squared, but this is n, and we know that that diverges. So there's another trick that we can use. We can simply write, what if this is 1/8 times zeta 3 minus 1, and so on and so forth. I'm not going to expand on that. So you can see that there are some ways for you to get by if there's a countable number of integer, if there is a countable number of outcomes in our set. But if they're an uncountable number, we can't use this summation anymore. We have to use an integral, and that's when things get interesting. So that's it.